Okay, hi everyone. I know I've been looking like an inanimate camera in the back of the room all semester, but this is me. I'm a clinical physicist at Erlanger in Chattanooga, and I'm going to talk a little bit about how we validated our Monte Carlo treatment planning calculation using small fields in a heterogeneous environment. So we've been fortunate enough there to be involved on the forefront of robotic radiosurgery treatment techniques with a machine called the CyberKnife. Stereotactic radiosurgery and stereotactic body radiotherapy involve treating tumors with an ablatively high dose per treatment. Unlike conventional radiotherapy that delivers 1.5 to 3 gray per fraction for several weeks, hyperfractionated treatments delivered a prescribed dose in 1 to 5 total treatments, with a dose that we've used anywhere from 5 to 22 gray, but it goes up higher than that in some other institutions. The ablative nature of this dose and the small radiation fields used with the CyberKnife require both highly accurate targeting and highly accurate dosimetry, with the latter point being the source of need for a project we completed that I want to talk about. So I'll share some background and then the details of the project while working in some connection points to the topics we've covered in class this semester. So the CyberKnife treatment planning system comes with two calculation algorithms, a pencil beam model called ray trace and a Monte Carlo model. Much more commissioning work has to be performed to generate the data needed to calculate dose using the Monte Carlo algorithm, and once that data is finalized in the treatment planning system, it's the responsibility of the medical physicist to ensure that data is tabulated and input into the TPS accurately. At the 6 MeV energy of the CyberKnife, charge particle equilibrium fails in highly heterogeneous environments, like with small tumors in the lung, and dose is not accurately calculated using the ray trace model. This is a two-screenshot picture in the TPS with a 20 millimeter beam delivering the same output in each image. And notice that the pencil beam method of ray trace overestimates the secondary lateral scatter of charged particles, showing a much higher dose at the point of measurement in the center of the simulated tumor, which is surrounded by lung equivalent material. Monte Carlo beam data is straightforward to verify in homogeneous material, but it's most applicable and far superior to ray trace in applications of heterogeneous environments. So to verify the Monte Carlo beam data in a heterogeneous environment, we came up with a procedure that accurately measures all 12 cone sizes of the CyberKnife, and then compare those measurements to the Monte Carlo TPS calculation. Previous publications had shown an incongruence between calculated and measured values of fields less than 20 millimeters in heterogeneous environments, and it was decided to use a double detector approach to verify all 12 cone sizes. A standard Farmer type ion chamber was used for cone sizes from 60 down to 20 millimeters as done in the previous work, and then a new to market plastic scintillation detector was used for field sizes from 15 millimeters down to 5. The benefit of the PSD is that its collection volume is a small solid scintillating material measuring 1 by 3 millimeters, and is therefore not subject to volume averaging effects like the air-filled ion chambers. PSDs are inherently different from standard air-filled ion chambers. Instead of collecting charge, they instead emit light that is directly proportional to dose. Now, there's some shrink-off effect in these PSDs, but having a dual signal calibration removes this unwanted charge from the measured signal, and the data that we were able to generate and the conclusion really of our work demonstrated our method for commissioning Monte Carlo beam data in a heterogeneous environment is accurate to within 3% for all 12 cones. And we were fortunate enough to be able to present this work at AAPM in 2013. So in conclusion, as part of the commissioning process for hyperfractionated planning, Monte Carlo TPS algorithms should be measured in homogeneous environments. Also, small field dosimetry requires small dosimeters. often using different signal collection means than standard ion chambers. And finally, Monte Carlo is the most accurate calculation algorithm and is most helpful in highly heterogeneous environments. So that's all I have. Thanks, and I hope to meet you all in person soon.